All right, today we're talking about the work and energy method. We are focused on planar kinetics, so we're taking whatever we taught during lecture 3, I think it was, and elaborating it for a wider array of problems. So we're considering things like rotation now for planar bodies. To start off, I have this illustration down here. This is basically a rigid body with centroid G. It is connected to a pin, and this location is given the name instantaneous center, IC. The body we have has mass. It has mass moment of inertia around G, and it has a mass moment of inertia around the instantaneous center. Now, in order for us to develop the kinetic energy formulation for this problem, we have to give it a velocity, we have to give it an angular, a rotational velocity as well. So here what we've introduced is this omega, which is our angular velocity, and we also have a tangential velocity, which I should probably correct to a more appropriate direction. It's probably going to look like this. So we have this tangential velocity component at the centroid G. So with this in mind, how does the kinetic energy formulation look like? T here will have two components. So right now we are focused on point G and we're analyzing the kinetic energy. The first component we want to look at is the tangential velocity. So we have the 1/2 mass Vg squared. This is from the earlier development, the earlier formulation that we talked about in lecture 3. And then there's a second component as well. If we notice, there is an omega that is being applied around the centroid G. What that tells us is there's another 1/2. This time, instead of mass, we have the mass moment of inertia around G, and then we also have omega squared. So this is really the addition, the new concept that we need to be aware of for work and energy method and planar kinetics. Now, this expression here is always positive, so whatever the value you get out of t should always be a positive value. So I'll just put this in brackets so you could always be aware of that. Now, another thing I could do is I can factor out the 1/2 omega squared. And this gives me, we get the following. Now, if we go back a lecture or two ago, we can remember the parallel axis theorem. And what this allows us to do is to shift the center of rotation that we're considering from G to the instantaneous center. So we could say this whole expression equals to. So whenever you're analyzing the kinetic energy of a planar body, you could either focus on the centroid G, and you could have the two components that you're analyzing, or you could basically just analyze the kinetic energy about the instantaneous center, and you will have a single algebraic component that you're multiplying and adding up. So this here is basically the instantaneous center that provides us with this expression. Okay, now we're going to look at another new work and energy formulation that we need to be aware of, and this has to do with potential energy. Potential energy obviously has a gravitational component. We're going to ignore that for now. It also has a spring component that we want to talk about right now. As you're aware, whenever we have a linear spring with coefficient k, we could describe the force for some displacement, going from S1 to S2. We could describe the force as k S2 minus S1. We can kind of describe this with the following expression, for which the energy formulation will be minus 1/2 K. And oftentimes S1 is the unstretched length, so we can pretty much ignore it from these expressions. We could set it to 0. So we could say typically S2 is smaller than S1. So that's where we get the compression from. So with this in mind, I want to introduce a rotational spring, which we get in many different mechanical systems. And to do this, we could probably look at an inverted pendulum. This inverted pendulum is connected at the very bottom with a pin. And in addition, we have this rotational spring that we're looking at, and it has a coefficient K theta. And what we do now is we go from position theta 1 to position theta 2. This is the direction that we're moving. And so now that we have a problem as such, what we want to do is we want to formulate the moment, the spring moments that is formed at the very base. This is MS that we're looking at. So obviously we have the coefficient of stiffness. This is K theta. We also have theta 2 minus theta 1. And like we said last time, most of the time theta 1 is the unstretched position, and you could set it equal to 0. Potential energy for the elastic behavior can be described as minus 1/2 K theta theta 2 squared minus theta 1 squared. And of course, theta 2 is generally speaking a compressed position relative to theta 1. So it could have a smaller value, and it really has, angles are a little weird. It really has to do with how you formulate it. Okay, so now we're going to look at the principle of work and energy. And what the principle of work and energy tells us, and this part is really the part that hasn't changed from lecture 3 up until now, is for some initial kinetic state, T1, we could have all these energy, all these work that's being added, all this energy that's being added. So we have sigma U, and this whole thing gives us a new kinetic state, T2. So we can go from some initial condition with all the forces, all the energies being added in, we end up with a final condition. So it might be a good idea to do an example at this point. And for this example, we are looking at a door, sort of like a gate that has a rotational spring attached to it, and we want to analyze the behavior of this gate. So this is the formulation that we have, the example that we have. And in addition, we're told that the rotational spring is undeformed when theta is equal to 60 degrees. So what happens is from this position, the mass is let go of, and this gravity that we have starts acting on this mass. And what we're trying to find out through this problem is some value for K theta such that the velocity for the gate becomes 0 when it reaches theta equal to 0. So whenever you have a problem like this, your very first step should be to draw a free body diagram. And for the work and energy method, free body diagrams generally don't require inertial components. We know that there is a W being applied at point G. We have the Fs, this is the spring force. We have the 60-degree angle. And if this length here is 1.2 meters, then half of it should be 0.6 meters. And so what I can also do is I can set this position down here as my datum, and I can say the vertical elevation going up to point G is y is equal to 0.6 sine theta. And theta is 60 degrees, right? So if datum is the final position when the mass drops and arrives at the datum, then what we're looking at is the initial position. So then we have this potential energy expression, Vg is equal to mgy. And I can say Vg is equal to, let's call this Vg1 because this is for the initial condition. So we have 25 kilograms. That is the mass of the gate. We have 9.81 meters per second squared. That is the gravitational pull. We have 0.6 sine 60. That is the vertical elevation for the centroid of the mass. And putting this all together gives us 127.4. So that's how much gravitational potential energy we have that we can consume through this behavior. And of course, when we arrive at the datum, Vg2 should equal to 0 joules because that's your datum position. You don't have any gravitational potential energy at the datum. That's a definitional concept. So that's one component of the potential energy. The other component is the elastic behavior. So we're looking at the different kinds of springs that we have. The problem told us that the rotational spring is undeformed when theta is equal to 60 degrees. So VE1 is equal to 0. This is the undeformed position as we see it in this schematic. We also have the final position, VE2, which is 1/2 k theta squared. Something that you need to be aware of whenever you're dealing with rotational springs is that rotation has to be expressed in terms of radians, not degrees. So if we are going to rotate by 60 degrees, we need to be expressing the degrees in terms of radians. And the easiest way to do this is to say 60 degrees is multiplied by pi. And what is the equivalent angle for pi in degrees? It's 180. So we divide by 180. So basically, we're not changing anything but the units. And this gives us pi over 3 radians. So that's what we have. Taking this, plugging it back into VE2 gives us pi squared over 18 k theta. And again, remember, k theta is unknown. We're going to have to do some exploring. With this in mind, what we could say is that kinetic formulations, the kinetic energies, are 0 to begin with. T1 is equal to 0. We're told that is the condition that we're told by the problem. So T2 is what we're also told by the problem. It's equal to 0. So we're going from some initial at rest position to some final at rest position. So I can take my work and energy formulation or the conservation of work and energy, and I can say these T's are equal to 0. And I have the initial potential energy, which is 127.4 joules, is equal to the final potential energy, which is pi squared over 18, k theta. And now I can solve for k theta, which gives me 232.4. And usually units for this kind of spring is Newton meter per radians. All right, so let's look at another problem. For this problem, we are going to look at a pendulum. This time the pendulum is in a lateral position. You can also think of this as a beam. And this is what the problem looks like. We are given this bar, this beam or pendulum. It has a weight of 50 pounds. At the instant that you're looking at, it is being rotated with an omega of 2 radians per second. And there is a spring that is being attached at point B. And the whole point of this spring is to slow down the vertical drop of the bar. So this spring is being attached to this position C, and C is basically a roller that's always moving along with the horizontal position of B. So it's always, this ensures that the spring is always vertical. So for this problem, what we want to find out is we want to determine the angular velocity of the bar for when it rotates 30 degrees clockwise. And another important feature I left out here is that K is equal to 6 pound per feet. So that's also important. Also, the unstretched length of the spring is 2 feet. Just lastly, I'm going to write down the problem statement. So that's really what the problem is asking us to do. First things first, it's the free body diagram. So I draw my initial position like I did last time. This is the initial position. There is a W that's being applied. There is a spring force that's pulling back up. Because this is a nice convenient horizontal line, I could say this is also my datum. And then I have the final configuration. So I kind of get something that looks like this. There is, again, a spring force that is pulling up. There is a 30-degree angle, and there is also this W that is being constantly applied. What also helps us here is to look at a couple of geometric information. One of them is this vertical clearance here, and one of them is this vertical clearance here. The smaller of the two can be described as 3, which is half of the length of the bar, so that's 3 feet, sine, what was the angle? It was 30 degrees. So we have 30 degrees, sine 30 is 0.5, so this gives us 1.5 feet of vertical clearance at the centroid. The larger value, this point here, is 6 sine 30. And this gives us 3 feet as the vertical drop. So we don't have any forces being applied other than just gravity doing its job. So this is another sort of conservation of energy problem. T1 plus V1 is equal to T2 plus V2. In this case, T1 is can be computed as 1/2 mass moment of inertia around the instantaneous center. If I look at my schematic here, where is my instantaneous center? It is this position here. So I can either look at my kinetic energy at the centroid, in which case I have to look at tangential velocity and angular velocity, or I can just look at the instantaneous center and my kinetic energy formulation just becomes angular velocity. So this is 1/2 mass moment of inertia around instantaneous center, omega squared. That is the initial omega that's given to us, is the 2 radians per second, plus we have the initial stretch of the spring. So we have 1/2 K, and I guess what is a good term to use for stretch? We could say this is it's U. So we have U2 minus U1. U2 is the 4 feet stretch. U1 is the 2 feet stretch. We're going to look at it in more detail. And then we can look at the right-hand side of the expression. We have 1/2. This is looking at T2, right? So we have 1/2 IIC omega 2 squared, right? So just to avoid the confusion with the subscripts, I can say this is 1 and 1 prime. Both of them are for the initial case. So we have on the right-hand side, we have omega squared. And I guess there is, we need to also account for the gravitational component. So we have the W, so that's mgy, wy, and this is the y that we're looking at. Let's put this all together. Here, looking at the left-hand side, we have 1/2. Instantaneous center about the end of a beam is equal to 1/3 mass L squared. That's a very common expression. And if you look at it about point G, the centroid, it is basically 1/12 mL squared. Okay. So putting this in, we have, and there is a angular velocity of 2 radians per second squared. So we have this. Then we have the spring, which is 1/2. The coefficient of the spring is 6 pounds per feet. So that's 6. Final stretch minus initial stretch. And when I say final and initial, these are both for the initial conditions. It's just that there is there's an unstretched length of 2 feet and there is a stretched length of 4 feet that we're starting off with. So that's 4 minus 2. We square this. And then we look at the right-hand side of this expression, which gives us 1/2, 1/3, 50/32.2, 6 squared. Omega squared is what we're trying to figure out. And lastly, we look at the gravitational component. Something else I forgot is when we look at this expression up here, there is also a 1/2 k U2 minus U1 squared, because the spring continues to get stretched as it goes down. So what we end up with on the right-hand side is something that's a little bit longer than what I had anticipated. We have minus 50 pounds for W. It's going down to 1.5 feet. That was the Y value that we computed. Whenever you are above the datum in your expressions, you'll have a positive energy. Whenever you're below the datum, you have a negative energy. That's why this is a negative value. And then we also have a plus 1/2, 6 being the stiffness. Now we are looking at U2, which is basically 4 feet plus 3 feet from here, minus 2 feet from the unstretched length squared. And that's it. We have the completed conservation of energy formulation. And when we solve this, omega at theta equal to 30 degrees should be 2.30 radians per second. That's it for this lecture. I hope, despite all its complications and all the new elements, you found this to be useful. Let me know if you have any questions in the comments. See you next time.